Hello again, and now I invite Jonathan LeBlanc from PayPal to do his presentation about secure payments or mixed communication media. Thank you.
Hi everyone, thank you. Thank you for joining me today. Again, my name is Jonathan LeBlanc and I head up Global Developer Advocacy for PayPal and Braintree. It's been about a year and a half since I've been back to Istanbul, and I travel around the world quite a lot throughout the year, and Istanbul is definitely one of my favorite cities to go to and go back to. So it's great to be back here. Now, I'm a nomad myself. I was born and raised in Canada, up in Montreal. That's where I grew up. Then I moved to the States, lived in Florida, California, Arizona. And you know, if I didn't travel around enough in my personal life, my job is to travel around the world and talk to amazing developers like yourselves. Talk at conferences, give hackathons. Pretty much we just travel around talking to people about different technologies. And as I've been traveling around working with different Wi-Fi signals, sometimes not so secure signals, sometimes working with some rapid prototyping on hardware, working with other people's hardware, I got to thinking, I'm transferring a lot of information, a lot of personal data about myself through these open Wi-Fi signals, because I'm one of those Wi-Fi hoppers when I go to a country where I might not have cell signal with. And when I'm transferring this information through, I have no idea how secure it might be, which is exactly the topic that we're going to be talking today. We're going to take a look at some of the most complicated data data that you need to secure the most, which is payments, and everything that goes into that. Identification, going into authorizing a payment. All of those details are what we're going to be looking at securing in interesting little ways. So what we're specifically going to be taking a look at on the consideration. Number one is our identity side. Now, a lot of us have seen all the worldwide hacks that have gone through where different companies, startups, all the way to large corporations have had all of their user records stolen and all of those records decrypted, or hopefully not, they store them in clear text. And I say hopefully not, even though most of the cases, that's what happens. They store information without encrypting it. We're going to keep talking, even though the power's out. So the other aspect that we're going to be taking a look at on the data communication side is actually looking at data in motion. So you can have data at rest, so that's data that we would store in a database, data that would be stored securely, and then we also have data in motion. And for most of the web and phone developers here, that would be most of the information that you're working with on a regular basis. That would be all your API messaging that you're sending through. So any data that you have in motion, that's being transferred from server to server, from phone to server, from between hardware, that's your data in motion. So we'll look at taking a look at encrypting data through those channels when a channel might not be entirely secure. And then finally, we're going to take a look into the payments architecture. So how do you, with securing the identity for securing a user's payments, securing the data process for transferring out address information or any personal information like that, then how do you actually process the payments on the user's behalf? We'll take a look at that, and then I'll finalize everything up with a few future-proofing aspects for actually trying to determine if the user is actually who they say they are. So let's start things off by looking at the identity aspects. Now, hopefully the power will go on very soon, or else this code will make absolutely no sense to all of you. But what we're looking at really when we're protecting identity is actually looking at account information. What we want to do is protect a user's account. And when we're doing so, what we really need to look at is protecting password encryption. So the password information that is being stored for a user, most of the time a lot of companies will have too much faith in their security architecture protecting their overall database. They're storing the information in clear text without any protection, without any encryption on the database, without any encryption of the passwords. And they wonder why, when their information is stolen, that it's so easy for these accounts to be compromised. The general rule of thumb in any security architecture is you should always assume that the possibility exists that your data will be compromised, that your database will be completely dumped, and that your user records will be stolen. So you have to try to mitigate those attacks by properly encrypting the passwords, restricting account access, and trying to slow down attackers as they are decrypting the data so that you can take appropriate actions to avoid accounts being stolen. All right. So when we're protecting identity through the password, through the actual password integrations, there's a couple of features that we need to talk about. The first one is salting. So how many of you here are familiar with password encryption, salting, anything like that? Okay, a number of you. Okay, most of the users, when they're coming to store their password, I'd say 90 to 95% of people, or at least from the leaked passwords, fall in the top 10,000 passwords. So 10,000 passwords represents probably about 90% of users that are storing their passwords. That's ridiculously easy to go through from attackers' standpoint when they're running a request in parallel to try to break that encryption. Now, what salting will do is take a potentially weak password, such as banana, and then apply some random alphanumeric character string on there, stick it together, and utilize that to produce a end hash. So the end hash would be some secure hashing, some secure mechanism. So let me put this in context. Two users come in, they both have that password of banana, and then I apply a unique salt to each of those and encrypt the data. The resulting hash at the end of the day, the alphanumeric character string that comes through, will be different for each one because the salt that I'm using is different. We're almost there. We get half of it. Oh, there we go. Hey! Okay, then we have to look at good encryption mechanisms. So you're not looking at your SHAs, your SHA-256s, any of those encryptions for speed. What you really want are encryption algorithms that are going to slow down the decryption process. So it actually takes some time. This is what you want. You don't want it to be instantaneous when you're actually processing, encrypting a password. You want it to take some time. So there are three overall encryption algorithms that are widely accepted in the security industry for encrypting passwords. bcrypt, scrypt, and PBK-DF2. We're going to take a look at practical implementations of bcrypt and PBK-DF2 because they're slightly different. bcrypt, scrypt, very similar. So the real reason that we do this is to protect against potential attack vectors. Things like rainbow tables, lookup tables, where we would have a stored hash of a password, and when an attacker comes in, steals all that information, they have all the time in the world to decrypt this data. So what they're going to do is use rainbow tables, lookup tables to compare the hashes that they have stored to the hashes that are in the database, and then they can easily pull those passwords from it. Dictionary attacks are using, as you might assume, using all the words in the dictionary to go through those for common words. It'll pull out quite a number of passwords from that. Now, if we kill off those potential attack vectors, all this potential decryption or trying to find a matching hash from an attacker standpoint is all out the window, so they have to build this from scratch, taking time, taking more resources. Power came on just in time for code. So here's what we're going to do. We're going to look at actually looking how these implementations might work. So how would we implement these? We're going to use a kind of a server architecture for this to show this. I'll write most of it in Node. Right now, all I have here is a simple HTTP request. So as you can see, HTTP request with an HTTPS URL. Real reason behind this is because there's a couple of ways that we can potentially encrypt the data here. And this is really just to show you where we're going. So we can use, we can use some built-in mechanisms to change the default scheme, default HTTP scheme in Android to HTTPS. So we can send a HTTPS request out from our phone to our server. We can potentially use something like public-private key cryptography, which I'll actually show you in a little bit when we're looking at securing some channels. You can use that, store the keys potentially in the key store, and utilize them like that, and push the information through. But for right now, we'll take a look at this for symmetry from the standpoint of a server-side architecture. So we push through some sort of password to our server. And this is the point where we can actually capture that data and start encrypting it. So bcrypt is a library within Node, or a package within Node that we can download from npm. npm install bcrypt, and then we can require it at the top of our Node script. Now, when we have our password, we can pass it to something like this function that you see here. And there's two steps to this. First, we have to create or generate a salt. So that's, again, hardening the password. So we generate that salt with a number of rounds. Now, the rounds are how many times the algorithm is applied over itself in order to harden it and build out a salt of an appropriate length. What happens is in this asynchronous request here, we get our salt back, and then we can start hashing. So we could call bcrypt.hash, passing in our password and our salt, and at the end of the day, what we get back is our encrypted hash. So the key, which would be our hash, we can store in our user record. We can store it alongside the username, the hash, which would replace the password. Password goes out the window. And then we would throw in our salt into the same thing. Salt really doesn't need to be stored separately because all it's doing is protecting against those rainbow table attacks, dictionary attacks, etc. It's really nullifying all these little cheats that a potential attacker would have to decrypt the data or to match the data and steal the password. If we do the exact same thing in PBKDF2, it's pretty much the same type of flow, but there's a few things to note here. A lot of people do like PBKDF2 as an encryption algorithm because it's memory intensive. So what this means is bcrypt, scrypt, when we're utilizing those, we can throw a lot of processing power behind it. The higher the processor, the faster, the more number of iterations we could run on decrypting the data or trying to break the encryption. But in the case of PBKDF2, it's memory intensive, so we need a lot of hardware. In order to decrypt passwords en masse, we need a lot of hardware. So if you have an attacker downloading data, that's what we would be dealing with here. PBKDF2 is built directly within the standard Node crypto library. So all we have to do is require crypto at the top of the page. We don't have to install it from npm. Then we can have a function just like we did before. We generate a salt with random bytes, specifying the number of bytes that we want the salt to be. And then from that comes back our salt. So our salt can then be applied to the hash and generating a unique hash for that password. So we pass in a password, the salt, the number of iterations. Now you see the number of iterations on bcrypt, PBKDF2, slightly different, massively different. But that's standard right there. And then 512 is the key length, the associated key length. And then what we get back at the end of the day is again, our hash. So we can store that in our database, and we can store the salt right alongside it. Now the way to properly actually tell if a password is correct, since all these encryption algorithms are essentially one-way hashes, so you can encrypt, can't decrypt. The way that it works is when a user has the registered account, so we store this information in the user account, right? The user comes back and tries to log in. We take their username and their password. We use the username to look up the user account record, extract the hash, extract the salt. Then we apply the same encryption algorithm to the new password that they logged in with the associated salt. And if the hashes match, we have a match. That's how you can actually do it to verify the hashes. And that's pretty much what it is to encrypt actual passwords. And this is going to protect in the cases of actually being in fairly unsecure or pretty much any environment. This is standards that should be implemented within password security for everything that we're building out. So next, let's take a look at this next phase, which is data in motion. Now this is one of the tricky bits that when I was trying to explore this, or starting to explore this, I was playing with these things, Estimote beacons. How many of you have played with Bluetooth Low Energy beacons or Estimotes before? Okay, a few of you. Now, essentially what Bluetooth Low Energy beacons are, they're broadcast systems. So these little beacons will broadcast at certain intervals saying who's around me. And it can connect to an application on a phone. It can connect through the phone itself or any other Bluetooth Low Energy device. And Any device that supports Bluetooth nowadays, with modern phones or anything like that, will support Bluetooth Low Energy. So the beacons in and of themselves, the reason why it became so prevalent to start talking about security on these is that they're insecure in and of themselves. They're little hardware beacons that just sit there that can be modified. It's the reason why the vast majority of the beacons just work as a broadcast system, why they just broadcast out what's around me instead of actually handling data. But there are systems that have been put in place for actually changing that. So utilizing beacons or Bluetooth devices as a bridge to an API endpoint. So what it's essentially doing is allowing you to be physically present in a store, for instance, connect to the beacon with my phone, saying I'm physically there, allowing you to check in, do things like making payments. There's a company called Locals with a Z at the end, or Z. And they were part of our Start Tank process. So this is a co-working space, a mentoring program that we have in London and Chennai. And what we essentially do is take payment startups that are building out, help mentor them, help build them up into viable businesses. Now Locals was taking beacons and doing exactly that. They're putting it on clothing or anywhere in the store where you can buy something. So you would take your phone, you would walk in and it would say, oh, you're in the store, why don't you check in? Allows you to check in, and then you walk up, say there's a shirt right here that I like. Oh, the shirt gives me information directly through the application saying, oh, this is how much it costs, this is how popular it is, etc. Would you like to buy it? Yes, I would. I click buy, it purchases it right there in the aisle. You don't have to go to cashiers, you don't have to do anything. You can just purchase it right there. That's the purpose of extending these beacons as a bridging system, because what they're essentially doing is hitting a endpoint. But they're not the most secure devices. They're hardware. You can modify them physically. You can adjust the messages that are getting sent out to send something fraudulent. So that's what we need to prevent. And the way that we do that is through a few different mechanisms. So first off, we can actually look at something called asymmetric key cryptography, or public key encryption. It's known as both the same thing. Essentially what that is doing is creating two sets of public and private keys. One for the sender, so me walking around the store, I would have my public and private key set, and one for the receiver, being the API endpoint. So let's say Braintree PayPal as the API endpoint. I'm making a payment through. So the way it'll generally flow is that I, as a sender, saying I want to log into the store. I want to send some basic address information or some basic login information to check in, to be able to pay. What I'm going to do is send a small little message through, perhaps a JSON object, perhaps a string, and I'm going to encrypt it with the recipient's public key. So the API endpoint, I encrypt it with their public key. Then I sign it with my private key. So you have the multiple keys going on. Then we pass it through the bridge, that hardware bridge. Of course. We pass it through that hardware bridge, and at the end, the API endpoint is going to take our data, take both the encrypted and the signed variations of that string, and they're going to decrypt the data. So the way that we actually will decrypt it, is with the recipient's private key. So private key, public key match on either side. And then we're going to verify it with the sender's, or my, public key. Now, realistically, where these keys are stored are on the sender side, on my side as I'm going through. Whenever I create a new user account, if I register within an account, I would have the private key and potentially the public key stored within Keystore, or some authenticated server side. Or I can have some public key store that I can make a request to get public keys for the recipient and the sender, and then I can actually pull those public keys automatically and do some basic verification, such as is the request coming from the application that's actually verified within my system. So that's essentially how this is going to work. So within the beacon sense, the general flow is we have our central device, me walking around a store with my phone. I connect to the beacon. Beacon allows me to connect to it, so I physically connect to it. It sends that connection request back to the phone. And then it acts as a bridge with my encrypted messages to the IP address endpoint, basically the end of my API. That is the entire process that we're doing with this key cryptography. The bridge in the middle, that little bit over there is the area that we want to avoid or have some encryption around, because this beacon might be the compromised little bit. And any hardware is pretty much the same that you'll be using. So again, we start with our code, pretty much the same as last time, sending the request or the post request over to our server. And for symmetry, we're going to actually look at how to do this within the node server. So when I have my user account set up, this is how we're actually going to create new keys for them. So there's this URSA library that we can just say, call npm install URSA, and that's going to install it. We require it at the top, and that's going to allow me to generate my RSA keys. So when I create a new user record, we create these. We can create these on the fly and store them in any mechanism we want. It might be secure storage within some server, some authenticated server out there. It might be within key store. It might be somewhere secure enough to be able to handle the keys. Then we have our recipient key sets, and typically these might be keys that are set up for each individual as it's coming through, so they can be revoked on an individual level instead of having one general key that is used on the recipient side, which might be compromised. So these two keys are set up before or during the registration of the user. And this one on the recipient side might be stored within their server in a secure area in a PEM file. All right, so let's say I have a message like this. I have some basic user information, some basic address information that I want to encrypt. I want to send through this piece of hardware. First thing that we're going to do is stringify that so that it can be encrypted and signed. Then I send through my encryption. So again, I use my recipient public key to encrypt the message. That gives me my encrypted data. Then my signed, and signed is like just a signature at the end verifying the source. So using the sender's private key, we'll go ahead and sign that. Now we have two variables that we, in turn, send through the beacon hardware. So the beacon hardware gets it. It has no idea what it is. It has no idea how to decrypt it. It doesn't have key access. It doesn't have anything. It might go to another attacker that might be some other API endpoint that they pushed it through. They have no idea what to do with it without the keys, without the data. So it's either going to go off into nowhere land, or it's going to hit the API endpoint that we actually need it to hit. And if it hits that, then we can start decrypting and verifying. So let's say we have those two variables that come through, the encrypted message and the signed message. Firstly, we can decrypt the message using the recipient's private key. So the server's private key, we decrypt it because it's basically a matching public-private key. Then we can take that decrypted message and we can push it to a buffer that is used for the basically the verification process. And then we can call, utilizing the sender's public key, hash and verify, passing in through that signed message that we sent through from the sender, as well as that decrypted message. And if they match, then we have a validated message. That means that we can start utilizing the decrypted message right here, validated from its original source, which would be the user walking through the store, trying to buy something. So they're sending information back over and over through this, and this is how you can do some asymmetric key cryptography. Now, obviously, there are some better methods for this. One of the biggest problems with asymmetric key cryptography is that it has restrictions on the size. It's rather unwieldy. As you saw, we send some basic JSON structures, and if you have any of the beacons out there that are sending messages back and forth, they're not sending a lot of data. They're sending basic JSON structures. So pretty much if you have 256 bytes that you're sending through, if you use 13 bytes of those 256, it's still going to send a 256 byte message. And since we're using RSA on top of that, it's going to add 13 bytes on top of that. If you go over 256, you'll have to find some way of concatenating those two at the end of the day. So it ends up being a little bit tricky. Now the good news is we're done with the vast majority of the code for a little bit, so it gives us enough time for that power to come back on. So realistically, the mechanisms that we want to use are HTTPS. We want to send everything through a secure communication layer. This allows us to also use mechanisms like OAuth 2 or OpenID Connect, which is essentially OAuth 2 with the user session management endpoints. How many of you here have worked with OAuth in any form? I'm quite surprised, and I feel your pain, whoever has worked with it. I've worked with it for a number of years. It was actually, I had been on the board for OAuth1 for a while back in my Yahoo days. It's an amazing way of actually sending through a verification message. So if you're communicating over HTTPS, what you're essentially doing is sending through an access token in the headers on every single message. Works great for identification. So identifying a user, it works great for actually sending messaging through, but it needs this overall secure communication layer. Now, the other mechanism that you can use is symmetric key cryptography, which instead of using a public-private key set, you share one private key between the multiple sources. So you can utilize that as well. That's probably if you have a lot more data that needs to be sent through and you have a better trusted source like HTTPS as you're sending things through in a trusted secure line, you probably want to use that. All right, now let's move into the payment side. Eventually this will catch up with me. On the payments side, how you're actually dealing with the payments. We now understand how to protect the user. We now understand how to send verification information like their address to verify their credit card information or to prove that the identity of the person. So we have these available to us in multitude of different methods or medias or over phone, over hardware. But for this one, what we're going to be looking at is the fun levels of actually looking at email or SMS. We're going to take our cues from this one. We run this global hackathon series called Battle Hack. We were here in Istanbul, I believe it was 2 years ago, or last year in 2014. But one interesting thing is we get to see a lot of cool payment hacks when people are building out on top of these hackathons. When we were at our last US-based hackathon in New York City, we saw a very interesting thing. I remember running it through with the guys that were building it out. What they essentially used was the Amazon Echo, and if you're not familiar with it, it's a little cylinder that can take voice commands. It's a speaker system, so it can take voice commands, spit it out to an API endpoint, and do something with it. So they were actually making voice payments through the system. Now, the way that they were doing it was incredibly insecure, but it got me thinking, what is a possible way of actually making this work? What is a possible way of doing this in a nice fashion? And the answer to that is something called tokenization. Now, if this was working, you would see this awesome variation of tokenization. So let me just explain this to you, how it's going to work. We have payment information, credit card details. We have verification things like the expiration date. Say that's sent towards PayPal, Braintree, the payment providers. And what is going to happen is when it hits those servers, all the user information, all the vital information about verifying and storing credit card information is going to be stored within their secure servers. And what's spit back to the user is this thing called a token. Now, a token is a alphanumeric character string. That looks like that. Perfect timing. So the token looks something like that. That's spit back, and it's going to be a reference for the user. Now, when you're storing payment references, what happens is you store that token instead of storing credit card information for the user. And trust me, this allows you not to have to deal with regulations like PCI DSS compliance, which dictates how to securely store information, handle information, where to store, and how to store hardware, and all of those details that you do not want to deal with. It's also why when you see leaks of information, password information that's leaked by companies, accounts that are compromised, why it ends up costing them so much. I believe the value that that's put on every single user record that is lost, the credit card information that's lost by the industry, is about $1,000 per record. So that's what you're looking at losing that data. So that's why you want to be dealing with something like tokenization. It's also what powers things like Android Pay or Apple Pay or Samsung Pay or all the pays. All the pays that are out there utilize tokenization. So the way that it's going to work is you're going to walk up with your phone, and let's say this is my kiosk over here. It's no longer my shirt, it's my kiosk. So I go to my kiosk and I go to pay, I tap to pay. That kiosk might be compromised. It might not be connected to a system. It might be sending the data directly to an attacker. I don't know. I trust the stores that I'm going to, but you never know. So let's say that is potentially compromised, or what we want to do is find a secure mechanism for making payments. So what's going to happen is the payment cards themselves are going to issue a token, one-time use or a short-lived token, to Android Pay or Samsung Pay or what have you. And they're going to allow them to do something called host card emulation. It's basically faking a credit card. So you have a virtual credit card that you can use to pay for, but it only lasts one time. So once you utilize this token once, it gets thrown away. What's really good about that is that it avoids cases where you actually have token reuse. So these tokens, if they're snatched after or during the payment process, they can't be reissued because the payment's already gone through, token's already been thrown out. That's why tokenization becomes so powerful. It's also the system that we and a lot of companies use. So Braintree and PayPal both use this system called vaulting. The way that we store the credit card information, and a lot of a lot of companies that take in credit card information and store it securely, how they do it is by storing things in their vault. So they'll store within their servers essentially all your credit card information, all your relevant details that are needed for verification. And they're going to put it in here and send you back a token. It might be short-lived, it might be one-time use. And you can utilize that token to make payments and do this host card emulation. Now, I said that after we get through this payments, there's going to be another interesting little bit that I love to talk about that's really orange, is extending the secure protection and how to actually determine maybe some more identity variables about a user. Because a lot of what we do is just about dealing with how to verify that the user is who they say they are. So I have a lot of fun with this in the hardware world. Now, a lot of you might recognize this, the Moto 360. I used to wear this religiously everywhere I went until I was actually going to the airports to come here. Got caught on the chair in the car, ripped the back right off, so I no longer have that anymore. But the interesting thing about this is it's a Bluetooth paired device to my phone. You know what else is also a Bluetooth paired device? A lot of stuff. My Bluetooth speakers at home, my car, actually my propane tank on my barbecue is actually hooked up to my phone that same way. So it's a Bluetooth paired device. Now, what's interesting about this is that you can actually utilize those paired devices to build up what's called bits of entropy on a user, on a person's identity. You're basically adding bits of identifiable information based on paired devices, based on unique MAC addresses and things like that, and you're utilizing that to identify the person. If they're in a home environment and they have all these paired devices, which I see on their account all the time, then they're more likely to be who they say they are. And that's easy to pull through from the phone. So all we really need to do is get the bonded devices. So we snatch the Bluetooth bonded devices, and then we can loop through them. Essentially what we're trying to extract here is the MAC address. When we can extract this MAC address, this can be used as another unique identifier for the user. And as we start pairing these devices, and we can use them just to build out the likelihood that the person is who they say they are, and maybe we don't have to put more identification systems in front of them, or logins, or what have you, before they have to actually make the payments. Then you have things like biometrics. Biometrics, and especially fingerprint scanners, have been coming through to a lot of devices. We've worked with Samsung on the same thing, essentially scanning thumbprint in order to log into your PayPal account. But the aspects of biometrics are really interesting in this, because I like to think of them as a second factor of authentication. So you utilize it, again, to build up bits of identifiable information for the user, and you use it to be able to log in. And at the same time, behind the scenes, there's a lot of secure aspects going on. There might be some GPS verification on regionality. There might be some hardware identification that's going on for determining a hardware fingerprint. Browser fingerprinting. All of these things we're capable of doing to build up bits of entropy, or the bits of identifiable information for the user. And at the end of the day, what we're really trying to do is building a secure connection no matter what we're doing. Our entire world is now connected. Our devices talk to each other. Our phone talks with everything else. So whether it be identification, identity protection, whether it be secure communications through potentially unsecured devices, whether it be through passing these payments through or building up identity profiles for the user, this is something that should be at the forefront of everyone's implementations of any sort of security. If you're working on prototypes, these are the types of things that you should be thinking about as you're building out a secure approach. So thank you very much for joining me, everyone. I appreciate your time. And I think we have about 8 minutes or so for questions if anyone has them. Oh, right down here. Oh, you have one up there? Go ahead.
Hi, I have two questions. Can passwords be taken in generating moments? And how do you parse information from send encrypted message?
I got the second part. So how do you parse an encrypted message? And what was the first one? What was the first question?
Can passwords be taken in generating moments?
I'm not sure I got that one. I can definitely answer the second one and we can go back to the first. So how you parse encrypted messages. Okay, so let's take this from 2 points, the password and data structures. So from the password side, you don't. What you essentially do is you have an encrypted hash for a password. Then what you do is take another password that you want to match against it. You don't decrypt the hash. You essentially take that clear text password and you encrypt it. And when you encrypt it with the same hashing algorithm, same salt, you compare the two, and then they should match. So you compare the hashes, the end hashes. For data encryption, for asymmetric key cryptography, so basically public-private keys, you will take the encrypted data it's going to be encrypted with the sender's public key, the recipient's public key, and when the recipient gets it, they decrypt it with their private key. So you're essentially using the keys to decrypt it, and then you're using the keys to, the other set of keys to verify it. So think of it like a letter with a stamp in it, and then inside is a signature. That's what you're essentially doing. Yes? So at the end of the day, so the question was, you don't, if you parse it. So essentially, you will parse it at the end of the day. You will decrypt the data when it comes to the server. You decrypt that with the keys, and then you get the clear text message. It's just a matter of keeping it encrypted when it's in transmission. You had a question over here, up in the front. Oh, over here.
Hello. Let's assume that we have all these encryptions and stuff, but we have to send data through the internet connection, and we have this public key and private key in the client side and the server side. So we're going to transfer the data with the encryption, and the server side is going to take the data from the as description and decryption. But the thing is, we still have to store the private and public key in the client-side applications, such as Android, which can be decompiled and can be found that secret keys.
Right.
And do you have any suggestion for the prevent that?
So there's always the risk of any of these keys being stolen on an individual level. So you can decompile and pull the information from KeyStore, but you would have to have access to it to be able to decompile it. So on an individual level, you might be able to rip out individual keys that can be utilized. So those are the issues within potentially KeyStore. Then other ways of handling this, and I remember back in my days over at Yahoo, we had built out this implementation for a JavaScript API. And we had a key store implementation. Now the key store, what they utilized was a lookup system for the key store. So it was hidden behind HTTPS with a secure lookup based off of OAuth 2. So if we can have an HTTPS connection, a secure connection to a public key store, public and private keys, and what we pass through to there is utilizing OAuth 2 or some like mechanism, an access token. So saying that the application is valid it was validly created on the side of the server. Then what we can do is we can securely pass back any particular keys, or even the end result of a key. So the encrypted message, we can send that back. So, a couple of mechanisms. On an individual level, it's definitely a possibility that the information can be stolen. You could store it securely on a server, if you have access to a server, or on an individual level, where you can send a secure communication, HTTPS communication down to a single server and transmit the information that way. Then you can securely store the keys in .pem files or something like that. Or you can have a public key store on the server side, on the API endpoint side, that can be used as a public and private key store lookup. That would be HTTPS and OAuth 2. So the question was, can that request be sniffed? If you have a secure connection, secure encrypted connection, where the connection is encrypted itself, and you're using OAuth 2 on top of that, where you're actually encrypting the data back and forth, no. Mm-hmm. Yes.
So, thank you for the presentation. I got two questions. First of all, there's limited number of hashes. So, is there any way to make sure that the hash and the password is the same? So, for example, cat and the dog has the same hashes, and if I write dog instead of the real password cat, so they'll have the same hash, and I will be able to get in the system. Is there any way to secure that?
On potential fault percentages, I'm not sure exactly what the fault percentages are with potential false identifications of hashes, but in the case of multi-use hashes, the vast majority of people are going to use one of those 10,000 passwords. But if we apply the salt, that would be unique on any individual level. Let's see. If we are going to find a unique way of hashing, I'm going to have to think on this one. I'm going to have to think on that one. Because there are going to be mechanisms that you can utilize for determining a false identification. Now, the false identification might be utilizing something like hardware identification. So if I'm using my phone, that's an interesting way. If I'm using my phone, what you can essentially do is use device fingerprinting or browser fingerprinting within a phone. Browser fingerprinting will pull out those bits of entropy on browser uniqueness to be able to determine how likely the browser is that I'm using right then to the browser that I've used in the past. So if we utilize information like that, browser fingerprinting, device fingerprinting, or basically Bluetooth paired devices build up an identity profile, how likely the user is who they say they are. Then we can, if we have an instance where it looks different, then we can maybe pull together a different form of authentication, a second factor of authentication. Or we can just implement second factor auth to begin with. Both of those should work. And the other question is, the most important vulnerability in these payments and password is human. So what can we do to secure their passwords from them, actually? You don't trust them. That's I don't trust people. So that's the general rule. You do not trust any user input. It's the same way why you don't just dump straight user input into a database, why you store it in a separate variable so that it's read as a string to the database, because otherwise you could do something like a SQL dump. So you can dump the entire database. So when you have a password coming in from a user, you salt it to harden it. So that's a way of not trusting what they're putting through. In the case of the data that's being transmitted through, you encrypt it on either side, and you give them specific ways of interacting. So you interact through the user interface, and you only send that information through. So you don't trust the users. Is the simple aspect. You don't, not so much as you don't trust them. You ensure that everything that they supply is double checked. Yeah. All right. Thank you very much. I'm sorry. I'll answer your question right now off stage, but I have to leave now. Thank you very much again, everyone, for all the time.